Hello everyone, welcome back to our lecture on tectonics. We're going to continue this conversation talking about hotspots. So you may have noticed looking at this map that this is a map of volcanoes and earthquakes around the world. And also that there's a lot of strange things going on here. One of them being that there's a lot of volcanoes that are nowhere near plate tectonic boundaries. They're right in the middle of the Pacific plate or out far away from a mid-Atlantic ridge, and earthquakes seem to be happening there as well. So what's going on? How are these volcanoes forming if they're not at plate boundaries? And the answer to that is hotspots. So hotspots are hot magma plumes that rise up from the mantle core boundary, and they bring this very hot liquid rock up to the Earth's crust, where it breaks through and produces a volcano. Importantly, though, that volcano stays in place, and that plume source stays in place as the plate moves with plate tectonics. So in the instance of Hawaii, a good example of a hotspot, the plate, the Pacific plate, is moving to the northwest. And because of that, you have a string of volcanoes that develop where the magma source is staying in place and popping up a new volcano until it finds a new path up and forms a new one. So the oldest volcanoes are further from this magma plume source, and you can see a line of volcanoes going all the way into Siberia here. So let's find out more about hotspots here.
So the Hawaiian Islands are geologically weird. They're formed by volcanoes, we know that. But wait, scrap that. They're formed by volcano. Just one. It's like an upside down chocolate kiss conveyor belt. There's a hot spot that forms a volcano, and then the plates move over the top, making the islands one by one. Bloop, bloop, bloop.
So how do these hotspots actually form and start off? Well, let's watch this volcano to find out. Watch this video to find out.
So if you scale things the way that we think that they scale, it looks like a lava lamp, right? You have some hot stuff rising, and it starts with a big blob, and then there's this long skinny tail behind it. The same physics happens in like nuclear bombs, right? The mushroom cloud is the same idea, right? There's that big buoyant plume, and then the tail, the skinny tail behind. So the idea is that Hawaii and the Hawaiian Islands and these other hotspot volcanoes are that tail.
Hold on. So, this mantle plume theory says that an unusual hotspot like Hawaii is just the tail end of that blob shape of solid rock rising through solid rock. That's it.
So then you might ask, well, where's the bubble? Where's the bubble? People have argued is that those bubbles are these things called flood basalts. This is good, I promise. This huge bubble just explodes onto the surface, and so most of Siberia is covered in lava flows, and most of India is covered in lava flows. Individual lava flows that are hundreds and hundreds of feet tall that cover an entire country.
Wow.
And
so that was, I mean,
that's
like,
the thought is that was the bubble.
Bubble exploding?
Yeah, that's that bubble exploding into the surface. This is the tail and the head.
Yeah. And then as the head gets higher and higher, the pressure is released. And that means that the solid rock is going to start turning from a solid into a liquid.
Yeah. And so that's what we call magma. And
so
the reason
have
it's
we
super
ever seen anything like that happen?
Never.
Would it be an incredibly violent event?
Well, this gets good. There have been many extinctions in Earth history, and many of them correspond with when we think these bubbles explode to the surface. So the most recent one was 40 million years ago, and it was tiny, like a thousandth of the size of some of these.
Yeah.
But the largest extinction in Earth history, the Perma-Triassic, happens during the largest flood basalt.
So yeah, let's hope that doesn't happen anytime soon.
Yeah, so that's a pretty cool idea that that these hotspots are remnants of these massive eruptions that formed these continent-wide magma or lava flows. known as flood basalts. So next we're going to talk about earthquakes. So you all have probably heard about earthquakes, and they can cause extensive damage. So an earthquake is just vibrations resulting from sudden displacement along a fault. We just talked about faults, that surface in which two different rock units move past each other. And so when that happens, you have a lot of vibrations that result, these seismic waves. And so there's two points for an earthquake that are important. One being the focus, which is where that slip along the fault actually occurs, and where that stress has been built up and then is suddenly released as that rock fails. And then there's the epicenter, which is the point on the Earth's surface that's immediately above the focus. And the damage that results from an earthquake usually depends both on the strength of the earthquake, but also the distance between the focus and the epicenter. So we can see all the distributions of earthquakes here, as well as their magnitude, how powerful they are. And the strongest earthquakes tend to occur at convergent plate boundaries, such as in the Andes and in the West Pacific. And because you have all that stress built up as these two plates are colliding, you can have very strong earthquakes that result. We can measure the strength of an earthquake with the Richter scale. So importantly, the Richter scale is a scale on a log curve. So it measures the amount of energy released by the earthquake, with each digit of the Richter scale moving up in a power of 10. So a magnitude 8 earthquake has 10 times as much energy as a magnitude 7. And the largest earthquakes we've ever seen have occurred in Chile, and they didn't even reach a magnitude 10. And so there are earthquakes all over the place every single day that are much smaller in magnitude, such as magnitude 4 or 5. But these larger magnitude earthquakes happen much less frequently, just because they require so much energy to produce. We can also categorize an earthquake based off of the Mercalli scale. So the Mercalli scale uses the effect or the impact of the earthquake rather than the energy. So an earthquake that causes more damage will have a higher rating on the Mercalli scale. For example, if there are houses that collapse and pipes that break, it would be a Mercalli class 9 earthquake. And so earthquakes have a number of different types of waves or shaking that result from them. The two main types are P waves and S waves, and you can see the difference of those types of waves here. P waves is short for pressure waves, and this is a compression and stretching of the material in one direction, and it moves through the material linearly, whereas S waves or shear waves move by that material moving sideways in the direction of movement of that wave and propagating through the material. Importantly, these P waves and S waves move at different speeds through rock, and we can use that fact to our advantage. We can see here, this is a seismograph that shows the amount of shaking in a particular location. And first we see that these P waves arrive. They tend to produce a little bit less shaking, and then you have the S waves arrive after them, and they produce a little bit more. And then lastly, you have the surface waves. These are waves that are, instead of compressing or stretching the material or shaking it, they're moving along the surface of the Earth. And so they take the longest amount of time, but can cause the greatest amount of shaking. And we can use that information to figure out where the earthquake is occurring. Because these waves are traveling at different speeds, the P waves, the S waves, and those surface waves, also sometimes called the Rayleigh waves or the Love waves, quite adorably, we can figure out the distance to the epicenter. For example, if we know that the P waves reached the seismometer 5 minutes before the S waves, we can see where these two lines are 5 minutes apart on this y-axis, and show that that earthquake probably happened around 2,000 miles away. And when we have multiple seismometers, we can triangulate the position based off of how far that earthquake had to be in order to have that distribution of P waves and S waves. And so we can find the epicenter with 3 different seismometers, or we can find the focus of the earthquake with 4 or more seismometers. Also, the soil that you're on has a big impact on the amount of shaking that you'll experience, not just the strength of the earthquake, but how consolidated the soil is below you. So bedrock does not like to shake very readily, and it will produce the lowest amount of shaking because it's so well consolidated. However, sand or silts are less consolidated and they can shake more easily. And then wetted sand and mud can produce the largest waves. And so you have to be very careful if you're, for example, building your house on a beach with sand that might be wetted, where you also might have an earthquake, because the shaking there can be particularly strong. And additionally, a process called liquefaction can happen. So liquefaction is a process in which fully saturated soil can turn into kind of a liquid, because all of those soil particles are being jostled around and can flow past each other because they're not being squeezed by gravity anymore. They're being shaken and vibrated and can move past each other like a liquid. You can see that here as this guy is shaking the ground with his weight. The soil can kind of flow. And this can have really dramatic effects. It can swallow entire buildings, or in this case, it can cause an entire car to sink into the mud, just because the soil has no resistance to completely flow around the object, and that more dense car just sinking in. I actually experienced liquefaction when I was kayaking in Greenland. You can see here, I run across the mud. Yeah, so that mud was so saturated and it was exposed to pressure and vibrations that it could actually flow underneath my footprints. Here's a map that shows the amount of shaking, or how frequently you get damaging shaking throughout the U.S. And you can see here that California and Alaska have some of the highest shaking rates because they're right on that plate boundary, the San Andreas Fault and the convergent plate boundary in Alaska. So you have a lot of shaking there and a lot of earthquakes. You may have noticed too that you have a lot of strange things going on in the Midwest as well. So what are causing these earthquakes? There's no hot spot here. There's a hot spot near Yellowstone, which we'll talk about in a later lecture. But what's going on down here? And what happens to be going on is that there's wastewater pumping. So whenever you have fracking and natural gas drilling, you have a lot of wastewater that results, and that water can be contaminated with different heavy metals and different chemicals that you don't want to just dump right into the drinking water supply. And so sometimes fracking companies will, instead of processing that wastewater to make it clean again, will just pump that water deep into a well far below the water table. Unfortunately, though, rock is more easy to fracture and shake and cause an earthquake if it has water saturated in it. And therefore, just small perturbations in the Earth's crust there can cause earthquakes to develop. And that's why you have earthquakes developing near Oklahoma City, where you have a lot of fracking. Since we've figured out what's going on and there's been legislation to try to reduce this process, then the number of earthquakes in this area has decreased. But it's definitely something to watch out for, that not all earthquakes are naturally caused, and they can be caused by just pumping groundwater back into the rock. The next thing that we're going to talk about are tsunamis. So maybe you've heard about tsunamis in the news. There was one that hit Sri Lanka very heavily a couple decades ago. So a tsunami is a massive wave that's caused by the movement of rock. And so when you have a geologic event that moves a lot of rock, you can have a wave develop, and that wave gets larger as you move closer to shore, and it can cause a lot of damage. So there's a number of different types of tsunamis. Maybe the simplest would be just a meteor strike. If you have a meteor that's hitting the ocean, it's going to produce a very large wave, and that wave can get washed up onto shore and produce a tsunami. The second type, maybe the most traditional type of tsunami when we think of them, is an earthquake tsunami. So whenever you have a fault or plate boundary where there's an earthquake that occurs, those rocks are moving relative to each other, and that displacement can push up or down a lot of water and produce a big wave that results. And that wave, after it's bulged up above the epicenter, will wash up onto shore and cause a tsunami. Additionally, you can have erosion tsunamis. Sometimes there are landslides that occur not just on land, but underwater as well. And so you can have large amounts of sediment and dirt that's moving down a slope, and that movement of material can cause a large wave. And maybe surprisingly, these are some of the largest tsunamis that we've seen, is when huge amounts of landslide material gets moved and forms these waves. And then the last type of tsunami that occurs are volcano tsunamis. So whenever you have a large eruption of lava from a volcano, that new material can explosively come out or and produce a large wave as a result that then washes on shore. As that wave gets closer and closer to the shore and the depth of the ocean gets shallower and shallower, that has an effect on the wavelength and amplitude of that wave. So the shallower the depth, the slower that the wave moves. It gets kind of caught up by the shore. And because it's moving slower, it kind of piles up against each other, and those waves get higher and higher. And you can see here when we look at the depth of the ocean. As you get to shallower and shallower depths, the height of that wave gets larger, and the speed also decreases. And you can get sometimes waves that are tens of meters high in the instance of some tsunamis. You can see here, this is the water surface height for a particular tsunami that formed right here, and it produced this upwards push of water, and then that wave propagated outwards from that location, and as it did, and as it got to closer to the shoreline, the height of that wave actually was higher than the initial height of that formed it, just because it's being propagated to larger amplitudes as it reaches this shallower water. And then also that wave propagates away in the opposite direction as well and can cause a tsunami on the other side of the sea or the basin there. So tsunamis can have very far-reaching effects and really devastate coastal communities. The largest tsunami that we've ever recorded happened in Lituya Bay, and it had a tsunami that released 55 million tons of material from an area right next to a glacier. And as that material gets moved into the bay, it produced a truly gigantic wave. So that wave ended up being over 750 meters high. You can only imagine what it would be like to see a wave of water higher than a mountain approaching you. And it washed all the way down this bay and had waves that were tens of meters high all the way along the length of the bay as that water wave propagated down. To put that in perspective, you can see the impact that wave had as it fell from this location into the water, and it produced a wave that washed all of the trees down over this entire mountainside. And that wave ended up being significantly higher than the Empire State Building. So tsunamis, while we tend to think of them as deep ocean events that start relatively small and then wash up and become bigger, they can also start as very large, sudden events as well. All right, so that just about wraps things up. So in summary, we talked about the layers of the Earth, the crust, the mantle, and the core, as well as the asthenosphere and the lithosphere. We talked about Earth's magnetic field and what causes that and the implications that it has. We talked about how that magnetic field can reverse and what that looks like in the rock record. We talked about plate tectonics and how mantle convection can move plates. And then we talked about plate boundaries and the interactions of faults along those plate boundaries, the strike-slip faults, the normal faults, the reverse faults. And then we talked about hotspots, earthquakes, and we just talked about tsunamis. So thanks everyone for watching, and I will see you all at the next lecture.